Okay, so previously we looked at double integrals. So we had an integral I that was the double integral of some function of two variables, f of xy dx dy over some region S, where S is defined in the xy plane. All right, how do you calculate the area of a circle? Okay, or how about the volume of a hemisphere or the volume of a sphere? Okay, well let's think. So we said before that this double integral I was the volume under a surface defined by xy coordinates that were in this region S. Okay, if we set f to 1, then this just gives us the area of the region S. So here is the region S in the x, okay, it's in the xy plane. And what we're doing is we're counting up all the little rectangles of width dx, dy, okay? So there's an area dx, dy. We're summing these all up to get the total area of S, okay? So if f equals 1, then I is just the area of the region S. Okay, so what's the area of a circle? So here's a circle, okay, of radius A in the x and y plane. And remember, the equation for our circle is that x squared plus y squared equals a squared, where a is the radius of the circle. Okay, so the region that we want to take, our S, is the circle. Okay. And we want to do the integral of dx dy, and we need to think about what the limits are. Okay, so this is the region S, okay, which is the circle. Let's think about doing the integral over y first, okay, and then we've got the integral, yes, like this, okay. We need to think about what these limits are. So if we do the integral over y first, that means we pick an x, so let's choose an x, maybe here. Okay, and we think about lines like this that go from the bottom of the region to the top of the region. Okay, so this is a line of constant x. And we need to think about what the y values can be. So down here, y, so if we rearrange this, we've got y equals the square root of a squared. So I'll just write it. Y equals plus or minus the square root of a squared minus x squared. Okay, this one corresponds to the minus sign. So here y is equal to a squared minus x squared. And here y is equal to a squared plus a squared minus x squared. Got a minus here, okay, and a plus here. Okay, so we're going to do an integral over y from this value minus the square root of a squared minus x squared up to this value, the square root of a squared minus x squared. Okay, and then we do the integral over x, which means we consider all such lines. Okay, and x here just goes from minus a to a. Okay, so our limit goes from minus a to a of x. Okay, and this will be the area of our circle. Okay, you could alternatively have chosen strips that were horizontal, like this, okay, and then the limits, you just need to think, because it's a circle, everything just swaps. Okay, so it'll be x equals minus the square root of a squared minus y squared to a squared minus y squared square root. Okay. So hopefully you can convince yourself that doing this integral, where y goes from minus the square root of a squared minus x squared to a squared minus x squared, and x goes from minus a to a, that spans the whole space, so this covers the whole region of the circle. Okay, what if we wanted, okay, we're not going to do this integral, okay, you can if you want, but we're going to come back to it in a second. What if we wanted instead the volume of a hemisphere? Okay, so we know what the equation of a hemisphere is. It's x squared plus y squared plus z squared equals a squared. Okay, so this is a surface. Okay, it's the surface of a hemisphere. So if z equals 0, if we're in the xy plane, then we retrieve the equation of our circle. We get x squared plus y squared equals a squared. Okay, so it looks like this. We've got x, y, z. And in the xy plane, we've got a circle of radius a. Okay, and if x and y are both 0, then we have that z is a. Okay, and then in between we've got this hemisphere. Okay, fine. All right, so what's the volume of the hemisphere? Well, we know that the volume under a surface is just given by the double integral on some region S of the function of two variables, dx, dy. Okay, and in this case our function, okay, which we could write as z, call this z if we want, okay, and we can pull out z here. It's the integral of the square root of a squared minus x squared minus y squared, okay, dx, dy. Okay, and when z is 0, we have that x squared plus y squared equals a squared. So it means that this region S is the circle of radius a. Okay, i.e. this integral we can do in this form as the integral of y first with respect to with this lower limit to this upper limit, and then we do the integral over x. Okay, this integral is non-trivial to do in Cartesian coordinates. Okay, so we're going to look at both of these integrals in a new coordinate system, and that's the polar coordinate system. So that's what we're going to look at now. So let me clean up the board, and we'll see how we can write these in a much cleaner form. Okay, and we can do the integral and find the area of a circle and the volume of a hemisphere. Okay, so let's think about a point on our circle. So here's our x and y plane. Okay, and here's a point on the circle. And it has an x coordinate and a y coordinate. Let's call it x and y. But alternatively, we can parameterize that in terms of a radius from the origin, r, and an angle theta. Okay, so this is a point on our circle. So we'll draw a little part of the circle here. Okay. So before we were thinking about Cartesian coordinates and thinking about our region S being divided up into little rectangles with width dx and dy. Okay, but we can ask, what happens if we change r by a small amount? So let's have r go into r plus dr, and let's change theta by a small amount. So theta goes to theta plus d theta. Okay, so if r goes to r plus dr, then we're at this point. Okay, where this length is just dr. And if we also change theta to theta plus d theta, okay, then we move around the angle also. Okay, and this will come back to the origin. Okay, this angle here is d theta. Okay, so we get this little region of area. Okay, and this length is just the arc length of a circle, so it's the radius r times the angle. The angle here is d theta, so the length of this here is r d theta. Okay, and just like you can add up all these little rectangles, you can add up all these little areas. Okay, but instead of the integral over dx and dy, you now integrate over r and theta. Okay, so our element of area is r dr d theta. Okay, and these are polar coordinates. Okay, so if we want to do the integral, we can either integrate over the region S the function of x and y dx dy, or we could change coordinates, change parameters. So we do the integral over the same region, okay, but now our function is described differently in terms of different parameters, r and theta. Okay, and our element of area, this ds, is now r dr d theta. Okay. So the region S is the same in both cases, it's the circle of radius a, okay, in the xy plane. Okay, so if we want to find the area of a circle, then we set g to be 1, okay, and we just calculate the area. That's the integral of r dr d theta. And we need to think about what the limits are. Okay. So in terms of r and theta, our circle, so let's extend our circle around. In terms of r, our circle goes from r equals 0 out to r. 0 to r, okay? And theta goes from 0 round to 2 pi. 0 to 2 pi. Okay, so we've got two integrals. We're going to do the r integral first, and then we can do the theta integral. Okay, so we've got 0 to 2 pi d theta of the integral of r dr between 0 and r. Okay, let's call the radius a, just to remove confusion between the r's. Okay, so we go from r equals 0 out to r equals a. Okay, so we're going to do the integral of r dr, which is r squared over 2. And we have to evaluate that between 0 and a. Okay, now the integral over d theta between 0 and 2 pi just gives us 2 pi. Okay, so this is equal to 2 pi a squared over 2. Pi a squared, the area of a circle. Okay, so this is a double integral to give us the area of a circle. Okay, and how do we calculate the volume of our hemisphere? So our hemisphere is defined by x squared plus y squared plus z squared equals a squared. Okay, and in terms of our polar coordinates, instead of x and y, we're now using r and theta. And we know that r squared is x squared plus y squared. Okay, so this is the r in the xy plane. So this is r squared plus z squared equals a squared. This is the equation for our hemisphere. Okay, so in terms of G, okay, G equals Z. Which equals the square root of a squared minus r squared. Okay, so our integral is over the region S of the function g, which is just the square root of a squared minus r squared. And now we've got our area element r dr d theta. Okay, and we know what the limits are. We go from r equals 0 to a, and we go from 0 to 2 pi in theta. Okay, so this region S is the circle in the xy plane again. Okay, so we can do the integral over theta easily. That's just 2 pi. Okay, this integral over r doesn't depend on theta, it's independent. Okay, so in this case it's 2 pi, the integral from 0 to a of a squared minus r squared r dr. Okay, and we can do this integral by saying so we let u equals a squared minus r squared. This means that du is equal to minus 2r dr. Okay, and our integral here we can write as 2 pi times the integral of the square root of u, and r dr is now minus du over 2. So we get a minus sign and our factor of 2 goes. And we have to think about the limits. Okay, so when r is 0, u is equal to a squared. And when r is a, u is equal to 0. Okay, so this is pi times u to the 3 over 2 evaluated at a squared and 0, and there's a minus sign at the front. Okay, so this equals pi a cubed. Oh, and yeah, we lost a 3 over 2. Okay, this is 2 pi a cubed over 3. Okay, which is half the volume of a sphere, as expected. Okay, so that's us having developed the apparatus to calculate the area of a circle and the volume of a sphere. Okay, and in the later section, section 6, we'll learn how to calculate the surface area of a sphere and other objects. Okay, so there's one last section to cover in section 4. Okay, so really well done for getting this far. Keep up the good work.